Hello and welcome back. Today is day 2 of 3 of inverse trig functions. Quiz number 6 happened today, so hopefully that's in. Reminder that required form number 2 is due soon. Take a look at it on Moodle and you'll find the date over here. And again, 2 classes later, you're expected to respond intelligently to one of your classmates' posts. Next class is day 3 of inverse trig. Then we have our review day and then the test. Look at the syllabus calendar to figure out exactly when you need to take that test. And I'll just point out there are no projects due between now and the test. So you have a little bit of a break before project 7 is assigned, which is right after the test. Okay, number 1. The first part of today's lesson is a review from our last class. We begin by finding all solutions of sine theta equals negative root 2 over 2 for theta between 0 and 360 degrees. Let's use the unit circle to help us. Okay, so we're looking for negative root 2 over 2 on the unit circle for sine. And remember, sine, is that the x or the y? It's the y. So let's write that equation over here. So here we wanted sine to equal negative root 2 over 2. And again, we've done this translation already, but you're not going to see exactly negative root 2 over 2 on this page. They will appear as negative 1 over root 2's, which is exactly the same thing. And so this problem really is about finding where the y-coordinate is negative 1 over root 2. So hunt around on the unit circle. See if you can find 2 places where the y-coordinate is negative 1 over root 2. So there it's 1 over root 2, but it's positive. That's no good. We want negative 1 over root 2 for the y. Nope, that's no good. That's also positive. Come down here. Negative 1 over root 2. I don't think I can erase the highlighting only, so we'll just point up there. And then the other one where it's negative 1 over root 2 and the y is right there. So we've got 2 answers to this problem. One of them is over there in the third quadrant at 225 degrees or 5 pi over 4, and the other one is here in the fourth quadrant, 315 or 7 pi over 4. And let's take a look. This one said, give me the answers in degrees. So from the unit circle, we can just write down our 2 answers, 225 degrees or 315 degrees. Recall the domain and range of our 3 inverse trig functions. They're listed here. The only thing that's not listed are the quadrants. So just taking a quick look, negative pi over 2 to pi over 2, which quadrants is that? That is quadrants 1 and 4. 0 to pi, that's 1 and 2. And then finally, negative pi over 2 to pi over 2, same thing as up here, just not including the endpoints, but it's still the same quadrants, so 1 and 4. 3. Let's find the value of inverse sine of negative root 2 over 2 by using the unit circle. Then we'll find inverse cosine of negative root 3 over 2. Okay, let's go back. So the first one we want here, inverse sine of negative root 2 over 2. But remember, we've already seen that that in the parentheses is the same as negative 1 over root 2. So in some sense, this problem is quite similar to the problem that we just did. It was the same number, right? Sine negative root 2 over 2. And it's still the y-coordinate that we're looking for. So it's still these 2 answers that we got. So let me just highlight, or I guess we'll circle these in green here. So we got the 2 answers, 225, and then over here was this 315. But this is an inverse sine problem. An inverse sine is very picky. And so we got to make sure we pick the right answer, and not just the right answer, but the right form of the right answer. And we know from our work last class that inverse sine of anything, we can call this guy t, is always trapped between pi over 2 and negative pi over 2. Although, was this a degree problem or a radian problem? Well, it doesn't say. So let's just do radians because we want to make sure we get more comfortable with that. So we're not allowed to just pick any old answer. You got to pick the one that's in either the first or fourth quadrant. So that eliminates this guy. That's in the third quadrant, so he's out. In is this one, 315 or 7 pi over 4. But the problem is that 7 pi over 4 is too big. It's bigger than pi over 2. So apparently what that means is that we're not supposed to go around the long way to 7 pi over 4. We're not supposed to go out this way. We're actually supposed to go the short way, negative pi over 4. So that's the answer to this problem. Okay, the other one we want here in this problem is inverse cosine of negative root 3 over 2. So let's write that up here. And just while we're here, I will point out the range of inverse cosine is between 0 and pi. So whatever we get, we better pick an answer between 0 and pi. So first and second quadrants is all we're looking at. We know that the cosine is the x-coordinate, so you just want the x-coordinate to be this magic number here. So we're looking for x's to be that number. Well, that's close, but it's positive. This one over here looks like a winner. Here's another winner right here where the x is that coordinate. This one is close, but it's positive, so that's no good. So we got two choices here. We have this one, and we have this one. But we just set up above that inverse cosine always lives between 0 and pi. So you can exclude anything that's not in the first or second quadrants. So that quadrant 3 example that we just pointed to is out. So that means that the winner is this here. Negative root 3 over 2 is the x, 150 degrees, but we're going to do radians, so 5 pi over 6. And that does live between 0 and pi. So that's what we wanted. Four, by using the unit circle, solve cosine t equals negative root 3 over 2 on the interval 0 to 360 degrees and on the interval 0 to 2 pi. Okay, so we can do that. In fact, we kind of did that. To say find angles whose cosine is negative root 3 over 2 is in some sense equivalent to this thing that we just did, where we found the inverse cosine of negative root 3 over 2. So how about we just start writing answers? So if we're doing, let's do the degree and radian thing separate here. So one answer that we just got right up above was 5 pi over 6. Super. And then the other answer was the one that we excluded. And remember the one that we excluded, we wanted this negative root 3 over 2 as the x. And we had a winner down here, but we excluded it before, but we include it now. So that answer is 7 pi over 6. So we've got two answers. And if you just go back and look at the unit circle, you can grab the degree measures of those exact same two angles. So I think the first one is 150 and the second one is 210. Hopefully that's right. 150 and 210. Okay, so how are you supposed to keep track which one is which? Well, when you're doing an inverse trig problem and it just says find this, there's one answer. Every inverse trig thing is going to have only one answer. But when you are solving an equation, you expect to have two fundamental answers. Two fundamental answers. So equations have two answers. Inverse trig expressions have just the one. Big difference. Number 5. By using an inverse trig function, solve that same equation on the interval 0 to 360 and 0 to 2 pi. We'll make use of something called the reference angle here. Okay, so let's give this a shot. We'll copy the equation, leave a blank space, but leave it in the right spot. Fill the blank space with the appropriate inverse trig function. Cancel. Okay, now you can use the unit circle, as we just did, to find that thing, but this one says use trig, inverse trig. So how about we use our calculator, and we will estimate our answers here. So inverse cosine of negative root 3 over 2. Okay, again, I hit sine, cosine, or tangent, so we think about the mode. Let's go ahead and do the degree one first. Hit enter, and we get 150. And down below, I'm going to put the radian version of life, but let's just stick with degrees for a little bit. And then we know one answer is 150, and we'll use the made up unit circle over here to find the other fundamental answer. So we know that 150 is this guy. And this was a sine, what was this? No, this was a cosine problem. And we know that cosine involves x, so apparently the x on this point is special. So we'll go straight down to the x value, which is this length. And you want the other point on this circle with the same exact x value, so clearly we just keep going straight down. That's the other x that we're interested in. So then we'll draw here and say that this angle is what we really want. And how do we find it? Well, I mean, we just did the same problem, so we know it's 210, but what if it were messy and what if we didn't know it going into it? So what we're going to do in order to find that purple angle, maybe I'll just erase the purple for a moment. But in order to find that purple angle, what we're going to do is figure out what the little tiny angle is in here, which has got to be the same as this little tiny angle in here. So let's find that one first. This one right here is definitely 30. So how do we do it? Well, we did 180 and then subtract off the answer we got. So if that's 30, then that means that this one is also 30, which means that purple, let's bring it back, must equal the 30 that we just found. That's called the reference angle, plus 180. That's this part plus this part. Try it again. There's the 180. There's 30 more, so there's our 210. Okay, same idea with radians, so let's go ahead and get the calculator to give us the radian version of things. You could retype it, you could just hit enter. 2.618. Okay, so finding the reference angle here is the same idea. Let's draw the same picture. 2.618. We got to know where that is, and you should know where it is without knowing that it's really the same as the 150. And again, if you know this is pi over 2 at the top, just know that that's about 1.5, and this is pi, which is about 3, and down here is about 4.5. So where does 2.6 live? Well, it lives in the second quadrant, closer to the 3 than the 1.5. So 2.618 is here, this angle. And same as before, we need to figure out what the, I guess we used red before. We need to figure out what this guy is down here. Same x value, because this is a cosine problem. And again, we're going to be interested in the reference angle, which is this tiny little angle in here. So this tiny angle is pi minus the 2.618. So let's find that over here. So it's about 0.5236, which means that if we were to draw purple, then this little angle here in black is exactly the same thing. So this is also 0.5236. And then to find the real purple angle, which is here down to here, we're going to add half a revolution, pi, plus the 0.5236. Pi plus the answer, 3.6652. So purple is equal to pi plus the black angle, which was 0.5236. And so that turned out to be about 3.6652. Okay, and so that's our other answer up here, 3.6652. Okay, so your book has more to say about reference angles than I do. They are important, and I'll just say it one time and then you can read more details in the book. The reference angle for any given angle is always the smallest angle between the one you start with and the x-axis. So in this case, we have this angle over here to green. The smallest way or the shortest way to get from this green ray to the x-axis is not to go back the way we came, but rather to continue on in here. And so that right there was the reference angle. If you started with purple, then the quickest way to get to the x-axis is not to continue, but rather go back the way you came. So that would be the reference angle. And you can look in your book for what the reference angle is when the angle's in the fourth quadrant or in the first quadrant. So read a little bit more about that. We'll move on to number 6. Now we solve our first trig equation where the angle is more complicated than just a single letter. By using the unit circle, solve cosine 2t equals -1/2 on the interval 0 to 360 and the interval 0 to 2 pi. Okay, so let's go ahead and use the unit circle. So cosine 2t is -1/2. Let's look at our unit circle. Okay, so I'm going to ignore the fact that this is cosine of 2t. I'm just going to call it cosine theta. Don't worry about the 2t business. Just some angle. We'll deal with the 2 at the end. So cosine is -1/2. Well, cosine is the x. So where is the x -1/2? So take a look at the unit circle and find the two angles where the x is -1/2. So hopefully we found them. The x is -1/2 here at 120 degrees, and also straight down below, the x is -1/2 at 240 degrees. So we have our two answers looking at the unit circle. So we said 120 and then 240. Okay, so we get 120 degrees and we get 240 degrees. But here's the deal. I called that theta, but it was really 2t. So instead of saying that theta is 120, now I'm going to come back and say that it's really 2t is 120 and 2t is 240. And then I'll do the same thing over here in another color for the radian version of things. You just have to replace, instead of 120, what is that, 2 pi over 3? And then down here, 4 pi over 3. And so the last step for each of these is to solve for t. And so we divide every one of these angles by what? By 2. So we get t is 60 degrees here. T is 120 degrees here. Over here we get, oops, we get t is pi over 3. And then t is 2 pi over 3. Okay, so we're done. We've got two answers in degree mode or two equivalent answers in radian mode. Problem is, we're not done. These answers are correct. The two answers we have in blue or the two in black, they're right, but it turns out there are more answers. And here's where we messed up. We are very used to the fact that between 0 and 360, we're going to get two fundamental answers, and that's it. Same thing for 0 to 2 pi. But the deal is that we were allowed to add 360 as many times as we wanted to. So instead of just saying 2t is 120 and stopping there, I could have said, well, I could just go around 360 or 720 or any multiple of 360, but I'll just do one single 360, which means that 2t in this case is 480. And if you divide by 2, now 480 is too big, right? It's not inside of 0 to 360. So that's why we would normally never add 360, because we just stop with our two fundamental solutions. But the last step here is to divide everything by 2. And if I divide everything by 2, then all of a sudden this 480 gets shrunk down and it comes into the range, or the domain, I should say. And we get 240, and that's another perfectly good answer. And then the same thing down here. Starting with the 240, we could have said, well, what if we just decide to add 360 to this guy? So in this case, we get what, 600, which is too big. But that's 2t. And so when you divide by 2, you get t is 300 degrees, which is not too big. It's a perfectly good answer, actually. So really, there are 4 answers to this problem: 60 degrees, 120, 240, and 300. 4 different answers to this problem. And so the procedure is written a couple of pages down in the notes packet, and we'll look at it together in a few minutes, but I'll just say it now. You want to add that 360 as soon as you find your two fundamental solutions. So as soon as we got the 120 and the 240, at that moment, we have to add the 360 times, times k. And same thing over here. We really should have added 2 pi k right there as soon as we got the fundamental solutions. And only at the end, after you've written in the 2 pi k or the 360k, do you do the little nitty-gritty details where you solve for t. Because otherwise you get these solutions that appear to be too big, but they can all of a sudden get shifted around and become acceptable solutions. So how about we fix these answers here? Let me leave those because those answers were okay. But down here, we could also have done 2t is 2 pi over 3 plus 1 complete revolution. So that means that, what do we get here? 8 pi over 3. That took way too long, but I'm tired. Divide this thing by 2, we get 4 pi over 3, another perfectly good answer. And then we can do one more. Or we could have taken the 2t and made it equal the other fundamental answer, which was this 4 pi over 3 right here, plus another 2 pi, plus another revolution. And this one is 10 pi. See, that was quicker. Picking up. So we get 2t is that thing. I should go back to sleep. That's not right, is it? Oh, it's not just 10 pi. It's 10 pi over 3. You guys knew that. 10 pi over 3. And then we can divide both sides by 2. And we get 5 pi over 3. And that's our other answer. So I'll highlight these guys in yellow. They're equivalent to the corresponding blue highlighted things. But we got 4 different answers here, not just the 2 that we're accustomed to. Okay, 7. By using an inverse trig function, solve these things on these intervals. Okay, so this is what I think is our most important technique, is using the inverse trig instead of using the unit circle, because hardly anything is on the unit circle. It just happens that we're looking at ones that are on the unit circle. But go ahead and write our equation, blank space, inverse trig in that blank space. Cancel. Look at this. Okay, so this is where we use the calculator. And we're going to type in inverse cosine of -1/2. And again, think about the mode. Let's go ahead and do the degree version first. And so in this case, we get 120. Happens to be a nice angle. That's fine. But it's not t equals 120. It's 2t equals 120. Or let's get the other fundamental answer, 2t equals. So again, you got to draw your unit circle to figure out where the other answer is. So if one answer is 120, we'll do this quicker because we've already done this problem a few times. And we know that this is a cosine problem, so apparently it's the x that's important. So here's the other angle that we want. And then we'll find these little angles in here. This is 60, therefore this is 60 by symmetry. Therefore purple is 180 to there, plus another 60, which is 240. And sure, it would have been easier just to grab 240 from the unit circle, but the point is that the numbers we get will hardly ever be on the unit circle, so we got to make sure we can do this with just the calculator. Okay, but here's where we stress the idea of adding the 360k. You got to put it right here, right now. In fact, let's not put that 360k there. Let's just refer to the problem that we did up above. This problem is now equivalent. You have 120, you have 240. You also have to add 360 to each of those to get to 480 and 600. And then finally divide everything by 2. So I'm just going to say see above problem at this point. get the other answers. And in terms of radian, the radian version of things, it's the same idea. I'll write down our equation that we had before. So that was this equation right here. And what we want to do is type this into the calculator, but this time we'll make sure we're in radian mode. Okay, so radian mode, and we get 2.094. Okay, and as soon as we have that, we got to make sure we can find the other fundamental angle. So 2.094, it's got to be in the second quadrant, right? Because pi is out here and pi is around 3. So we want an angle that's about 2. So there's your 2.094. If that point is important because of the x, then the other important point is straight down from that one. So we'll draw the purple. And then we'll say that, again, we got to find the reference angle. So this little angle in here must be pi minus the 2.094 that we just got. So that's a little green angle, so we can type that. So that's about 1.047, which means that this other green thing is also 1.047, which means that purple must equal the half a revolution to there, which is pi, plus the little green angle, which we said was 1.047. And we get 4.188 or 4.189. So 2t equals 4.189 is the other fundamental equation. So you got the two fundamental equations there and there. And definitely you're going to divide each of those two numbers by 2, but before you do, I would say we should add this 2 pi to each of them. .094 plus 2 pi, or 4.189 plus 2 pi. You can type those into the calculator, and then you'll have your 4 equations. 1, 2, 3, and 4. And you're going to take each of those right-hand sides of those equations and divide by 2, and you'll have your 4 different values of t, which should agree with the 4 values of t that are highlighted there in yellow. So those are the exact answers. We hardly ever can hope for exact answers, so we can use the calculator to do these. Okay, so let's finish this one here and we'll just get the answers. Okay, so I'm going to be lazy and not use all the digits. Plus 2 pi. And then the same thing for the 4.189. Okay, and then we're going to divide each of these numbers by 2. So we get t is approximately equal to, just type each of them in here. So 2.094. And then what's the next one? 4.189. .8377. And then one last one, 10.472. Okay, so those are our 4 values of t. And I'll just round to the 100th on each of these. Okay, so when we're ready, move on to the next page. Number 8. solve cosine 2t equals -1/2. I feel like we've done this already. The only difference here is that instead of finding specific solutions between 0 and 360 or 0 and 2 pi, we need to find all the solutions. So let's just go back to the fundamental solutions. So for the degree version of things, we had 2t equals and 2t equals. So I think we had 120 degrees and 240 degrees. Let's make sure that that's what we wrote here. Yeah, 120 and 240, we see those. And then we'll write the radian version of the same thing. So what is 120? So that's 2 pi over 3, and then the other one that we had was 4 pi over 3. Notice that each of these is equal to 2t, not just t, not just theta. Okay, and at this stage, before we divide everything by 2, I'm going to add here in red our plus 360k. Plus 360k. Same thing over here, but now it's 2 pi in radian version. And so here we divide everything by 2, and we'll be done as soon as we divide everything by 2. So this one becomes t equals, so divide the 120 by 2 to get 60, divide the 360 by 2 to get 180, and then there's a k. Or in the second equation, divide the 240 by 2, and then divide the 360 by 2. So that right there is the complete collection of solutions to the equation cosine 2t equals -1/2. If, for example, you plug in k equals 0, then we get 60 and 120. Two answers that we got on the previous page. You should check that. If you plug in k equals 1, then this becomes 60 plus 180 or 240. This guy, when k is 1, becomes 300. Those are the other answers that we got. And there are many more. You could pick k equals 2 or 3 or 76. And then we'll play the same game in the radian version of things. So we'll divide everything by 2. So divide the 2 pi over 3 by 2, we just get pi over 3. Plus divide 2 pi k by 2, we just get pi k. Or, second equation, divide the first fraction by 2, we get 2 pi over 3, plus divide the 2 pi k by 2, we get pi k. If you plug in k equals 0, we get pi over 3 and 2 pi over 3. Those were two answers. If you plug in k equals 1, then this becomes 4 pi over 3. Plug in k equals 1, and this becomes 5 pi over 3. Those are the other two answers that we got before. Okay, number 9. By using the unit circle, solve sine 3t plus 2 equals -√3/2 in degrees and in radians. Okay, first observation, the angle, the thing in the parentheses, is getting more and more complicated. But that's okay, we'll handle it at the end. The next thing is that it doesn't say from 0 to 360 or 0 to 2 pi. And if it doesn't give you that kind of restriction, then you can expect you're going to be giving answers with k's in them. Okay, so let's just write it this way. Sine of something complicated is supposed to be -√3/2. So I'm just going to write that on our unit circle. Sine of something complicated is -√3/2. And we said that sine was the y value, so we just need y values to be -√3/2. Let's see if we can find them. Okay, y value of -√3/2. So that's close, but that's positive. So I guess we're looking down here. Y value -√3/2. Looks like we have a winner here and another one right over here. So the answers, running out of highlighters, looks like 240 or 4 pi over 3. And then over here, 300 or 5 pi over 3. So that's what we're going to write from the unit circle. Okay, so we got 240 and 300. in the radian versions of things, 4 pi over 3 and 5 pi over 3. Okay, so these numbers are floating at the moment. Normally, this is just t equals. In the last problem, it was 2t equals. In this problem, it's 3t plus 2 equals. So we need to copy that a bunch of times in front of each of these. Okay, now you might be very tempted to solve each of these 4 equations for t and then worry about the k business later. Avoid temptation. At this moment, and at exactly this moment, is when we need to add the 360k's or the 2 pi k's. We have to put it here. Put it anywhere else and it'll be too late. Again, I'll show you a procedure, I think it's on the next page, where it says at the very end, solve for t, but not until you've put in the 360k's or the 2 pi k's. Got to do that early. Okay, and now here, we're going to solve each of these for t's. So this first equation, we will subtract 2 and then divide by 3. So subtract 2, I guess the 2 goes with the 240, so that makes it a 238 plus 360k. You're not subtracting 2 from everything, you're just subtracting 2 from both sides of the equation, and then you're combining like terms. The 2 goes with the 240 because they're both just numbers. The 2 does not go with the 360k because the 360k has a k in it. And then we take this equation and divide by 3, and we get 238. But here we do divide everything by 3 because that's the impact of dividing the right side by 3 is that each term gets divided by 3. So that's it, 238 over 3 plus 120k. That's the first set of, it's the first infinite family of solutions. We'll do the other one here in purple. I'll do this one 2 steps in 1. So subtract the 2 and then divide by the 3. So subtract 2, we get 298. And then we divide both sides by 3, and so this guy gets 298. And then divide both sides by 3, and so that again becomes a 120k. Okay, same idea over here. We're going to subtract 2 and then divide by 3. So subtracting 2, there isn't a whole heck of a lot to do here. I guess the 2 goes with the first part, but it's messy no matter how you handle it. And then divide everything by 3. So let's divide everything by 3. 4 pi over 9 minus 2 over 3, dividing everything by 3. 2 pi k over 3. Okay, and then the same idea for the last equation. So we'll do both steps in 1 here, so we get t equals. So we'll subtract the 2, and we'll divide everything by 3, including this red thing. By using an inverse trig function, solve this equation in degrees and in radians. Okay, so this one is quite similar to the one right up above, so maybe this is a good time to pause the video and come back after you've given it a good shot. You should end up with 4 equations. They should look quite similar to the ones that we've got here. They should all say t equals. 2 of them should have degree things in them. 2 of them should have radian things in them, and they should all have k in them. So pause the video and come back when you're done. Okay, hopefully you didn't pause the video for too long, but I realized I did not read very carefully. Not only is this problem similar to the one above, it's exactly the same as the one above, except in the directions. The equation is the same, but here we use the unit circle, and here we're supposed to use an inverse trig function. And again, I think that this procedure is the most important for the day, is solving a trig equation with an inverse trig function. So let's copy this thing. Again, leave the telltale space. Inverse trig function, both sides. Cancel. Oops, don't be overzealous about canceling. And then what's left is just this 3t plus 2. So this is the part where we got to use the calculator. Okay, so we're typing in inverse sine of minus root 3 over 2. Okay, let's do the degree version of things first. And in this case, we get negative 60 degrees. That's fine. Normally, when you use the calculator with an inverse trig button, you won't get a nice number, but this one was. So we get negative 60 degrees, no problem. And then we have to think about symmetry to find the other fundamental answer. So negative 60 degrees is down here in the fourth quadrant. Okay, and so this is a sine function, and we know that for sine, it's the y value that's important. So apparently that y value is important. Here's the other point on the unit circle where it's the same y value. So we got to think about reference angles here in order to find the real angle, the purple angle. I guess we know that this little thing in here has to also be 60 using the symmetry, which means that purple must be 180 plus 60. So we get 240. And so that'll be our other equation, 3t plus 2 equals 240 degrees. And I'll say that these are not exactly the same as we got before. The 240 sounds familiar, but didn't we have 300? We never had negative 60. Yeah, we had 300, but 300 is the same as this, just going the other way. It's totally fine to replace the negative 60 with 300, but I would just leave it as negative 60. And so that means that the next step, which I'm not going to do here, is to add the 360k to both. And then you're going to solve for t. And I'm not going to do it because we did exactly that right up here. But the difference is that instead of having a 300 down below, we're going to have negative 60. So this 298 is going to change. It'll be negative 60 minus 2. It'll be negative 62. So this will look different, but everything else will look the same. So we're not going to repeat, and it's totally all right for you know, the fundamental answer to look different. But let's go ahead and do the radian version of things. So same calculation, just change the mode. So we get negative 1.047. So 3t plus 2 is negative 1.047. So to find the other fundamental solution, got our unit circle. We know that if we go up to the top, it's about 1.5. So down to the bottom must be negative 1.5 going clockwise. So negative 1.047 is in here somewhere. Well, of course it is. It's the same as the negative 60 degrees that we found before. But even if you didn't know that, you should be able to figure out roughly where it is. Certainly should know it's in the fourth quadrant. And just like before, this is the important point. It's a sine problem, so we need the same y value. It happens here. We'll draw it in purple. In order to figure out the real purple angle, we need to figure out this green angle, but oh gosh, that's got to be 1.047 by the symmetry. And so that means that purple is half a revolution going to here is pi plus the green angle 1.047. So that's half a revolution plus the green. Okay, and so we can type that in the calculator. So we can do second pi plus 1.047, 4.189. Okay, so we've got our two fundamental answers here, 4.189 and negative 1.047. I'm not going to do all the details here finishing this one, but I'll just say that what we need to do is right, 3t plus 2 equals negative 1.047, or 3t plus 2 equals the 4.189. And then instead of adding 360k to each of these, we're going to add 2 pi k. Okay, and then let's go ahead and let's finish these. I think I might have said I wouldn't finish, but let's just go all the way through to the end on this. So we're going to subtract 2 and then divide by 3. Okay, so we get t equals, all right, so subtract 2 from both sides. So negative 1.047 subtract 2 is a negative, well, we'll just say 3t equals negative 3.047 plus 2 pi k, and then divide everything by 3. And here the calculator will come in handy. That's that, and then we might as well take the other guy and divide by 3 as well. 2 pi divided by 3. So you can write 2.094, or you can just leave it. I personally like to leave it with the pi's in it, but either way is okay by me. So what do we have? Negative 1.016 plus, and then this guy also gets divided by 3. That's the one answer. Or I could do this guy. And let's see. So same idea as before. Subtract 2 from both sides. And then divide everything by 3. So that's about 0.73. And then plus the 2 pi k over 3. Okay, when we're ready, next page. 11. For the rest of this section, all variables are in radians. Let's find the first 4 positive solutions of cosine of 2/3 theta minus 1 equals 0.2. Can we use the unit circle? We'll check our answers by looking at a graph on the calculator. Okay, so let's give this a shot. Okay, so 0.2 is not going to be a nice angle on the unit circle, so definitely going to want to use inverse trig here. Let's just jump to the part where we cancel the inverse cosine on the left and say 2/3 theta minus 1 is equal to inverse cosine of 0.2. So we'll use the calculator to give us our approximation here. So it doesn't say degree or radian. I'm not going to do both. I want us to get comfortable with radians, so let's do this in radians. 1.37. And then a real quick unit circle to figure out where the other fundamental answer is. So we know that 1.5 is roughly up here. So 1.37 must be here. And this is a cosine, so it's the x value. The x value is the same at this point down here. So let's find the other answer, which is to go from here all the way around. Definitely that's 2 pi minus 1.37. So about 4.91. Okay, so we've got our 2 fundamental answers here, 2 fundamental equations that we're going to write. Okay, so then let's write those 2 equations. So we get 2/3 theta minus 1 is equal to the 1.37. We knew that already. And then the other one is, where'd it go? 4.91. Okay, and at this moment, and before we do anything more to find theta, we have to do this plus 2 pi k. Okay, and now we got to solve each of these equations for theta. So let's go ahead and solve for theta. So we'll add 1 to both sides. And then multiply both sides by 3 over 2. Okay, so if we do 3 over 2 on the second term, the thing with the k in it, we just get 3 pi. I think that's right. And then we need the 2.37 times the 3 over 2. And let's go ahead and make this bigger again. Okay, so what are we doing here? 2.37 times 3 over 2. So 3.56, we'll say. Okay, so that's one answer. The other one is going to come from this equation. So add 1 to both sides. And then we'll go ahead and multiply both sides by 3 over 2. First one we'll do on the calculator. This is going to be the same 3 pi k that we had before. Okay, so we're doing 5.91 times 3 over 2. 8.87. So I'm doing all kinds of bad rounding things. Don't do what I'm doing. Use more accurate numbers than I have. But I'm trying to get home. Okay, so we've got our two equations that give you every single solution to the original equation. So all we have to do is find, it says the first 4 positive solutions. Is that what we're after? First 4 positive ones. So so let's just start picking values of k. For example, you know what, maybe we can even make a chart here. So let's make a chart. So we're going to have a row for k, and then we're going to have a row for the first green one, 3.56 plus 3 pi k, and then another row for the other green one. Okay, so for example, if k is equal to 0 or 1 or 2, so if k is equal to 0, then, well, that's easy. This is just 3.56, and this is 8.87. So those are the first 2 positive values of theta. Maybe I'll add in here, this is theta equals in both rows. You could also try like a -1 in this table. Go ahead and plug in and convince yourself that you'll end up with negative numbers there. So these are really the first 2 positive ones. Okay, so then we can come back here and say, hey, well, what if we just take the 3.56 and add 3 pi, because we're picking k equals 1 in this case. So we get that number, or we could have done the 8.87 and add 3 pi times 1, which is that number. So let's write down those two. And 18.29. Now we're done. We've got the first 4 positive ones, but it's not hard to find any more. Let's do second enter, and then instead of just doing 3 pi times 1, what if we do 3 pi times 2? So there's the next positive answer. And this 8.87, instead of doing 3 pi times 1, we could have done 3 pi times 2. We get the next one. So we'll go ahead and write these two in. 22.41 and 27.72. Okay, and then it says we're going to take a look at a graph on the calculator. So here's the graph we're going to look at. We're going to graph the left-hand side. Y1 equals the left-hand side, and Y1 equals the right-hand side. Let's do the right-hand side first. Y1 equals 0.2. Easy. Next one. It's the more complicated left-hand side. Cosine of 2/3 theta, that's x, minus 1. Okay, let's go into the window. So looking at the answers we got, the biggest one was up there at 27. So let's go ahead and go from 0 to 30 maybe. And we'll go by maybe 5s. Okay, and then in terms of the y values, well, you know, cosine bounces between -1 and 1. So how about we just look -1 to 1. Okay, so we're going to graph. First thing we'll see is that horizontal line at point 2, and then we'll see our cosine thing bouncing up and down, up and down. And if we've done this right, then hopefully we see 6 intersections on the window that we've chosen. 1, 2, 3, 4, 5, 6. Hooray. Let's see if we can use the intersect command to find a couple of these. Second calc, number 5. First curve, you just hit enter. Second curve, you just hit enter. I'm going to hold this left arrow. Well, I can't hold it, but I'm just going to keep hitting the left arrow until I get close to that first point of intersection. Okay, that's close enough. And then we'll hit enter. And hopefully it says 3.56. It does. So that's the x value right there, which agrees with the first number in our table. Let's move the table a little bit. Okay, so that's one intersection. We'll do second calc, 5. First curve, enter. Second curve, enter. Let's go ahead and move over to another point of intersection. So how about let's skip ahead. Let's do this one, and then I'll show you the shortcut. So hopefully this one says 8.87. Great. That agrees with the next number we have in our table. Okay, and then we can do one more, but let's do it without all the funny arrow business. So second calc, 5. And first curve, enter. Second curve, enter. Now I want the answer that's near 22. You can see maybe this hash mark right here is around, so what did we say? It was up to 30 by 5. So this must be 24. So if I just hit 24 instead of playing around with the arrows, then it'll just zip to the 24 and find me the closest answer, which is this 22.4, which is what we got before. Okay, moving on to number 12. What if the equation isn't of the form trig function equals number, but instead has more numbers floating around it? Let's use inverse trig to solve 2 cosine 4t equals negative 1.5. So the first step, and again there's a process, it's right down below, is to make it look like trig function equals a number. So let's divide both sides by 2. Now it looks like trig function equals number, and we can solve it in the same way that we did up above. Okay, so let's just get this to be a decimal. All right, and then we'll take the inverse cosine on both sides. Then we'll use the calculator. Again, I want radian mode just so we can practice with it. The problem doesn't specify. So about 2.42. Okay, that's fine. That's one fundamental solution. We got to find the other one, so a quick unit circle should find it for us. So at the top is about 1.5. At the left is pi, which is around 3. So definitely this angle is in the second quadrant. So 2.42 is there. And this was a cosine, and cosine is x. So the x coordinate is important. The other point on the circle with the same x coordinate is that one. And we want to find what the real angle is. First, we need to know what this green one is because that's the same as this green one. So green is definitely pi minus 2.42. 0.722, say about 0.72, which means that purple, I haven't drawn purple yet, purple is this guy, must be half a revolution, pi, plus the extra green, which is this 0.272. So pi plus 0.272. So about 3.86. So that's our other fundamental answer. Okay, at this moment and only at this moment is when we need to put in the plus 2 pi k. And then finally, at the end of the process, we solve for t, which in this case means dividing both sides by 4. Okay, so I'm going to use the calculator in a second, but let's go ahead and divide the second term by 4. So I think that just gives me a pi k over 2. And then we'll take our two numbers and divide by 4. So that's it. Those are our two answers. Okay, 13 is this long-awaited process I've been building the suspense for. Basic approach to solving trig equations is 1. Isolate the trig function. What that means in this problem was dividing both sides by 2 to get the trig function by itself. So that's the isolate the trig function part. Step 2, find one value of the angle by using an inverse trig function. So we used inverse cosine here and typed it in and ended up getting one value of the angle, 2.42. Then, number 3, find the other fundamental value of the angle by using the symmetry of the unit circle. So we did that over here on the top right. We used our symmetry, we had greens and purples, and eventually with a lot of calculations got 3.86. And so our two fundamental angles were the 2.42 and the 3.86. Number 4, add 2 pi n, we've been using k, it doesn't matter what letter you use, to both values of the angles that you found. So we added 2 pi k here and here. We didn't divide by 4 first, we added 2 pi k first. And then lastly, and that's an important word, solve for the variable. So solving for t seems like the first thing we should do, it's actually the very last thing to do. And then we've got our answers. 14, use the above approach to solve 3 tan 2x minus 1 plus 7 equals 2. This is our most complicated trig equation to date, so let's go through the whole process. So it says first isolate the trig function, that's this piece. So the things that are nearby that need to move are the 3 and the 7. So first we'll subtract 7. And then we'll divide both sides by 3. And the trig function is now isolated. Next thing to do is use an inverse trig function in the calculator in order to find one fundamental angle. So in this case, it's the inverse tan of negative 5/3, whatever that is. Okay, so we'll type this on the calculator. Again, make sure you know what mode you're in. I'd like us to practice radians unless otherwise stated. So about negative 1.03. Okay, at this moment we need to think about symmetry. We need to think about the unit circle. Okay, where is negative 1.03 as an angle? Okay, we've done this a few times. Negative 1.5 is at the bottom, so that must mean negative 1.03 is in here somewhere. Okay, thinking about symmetry. Well, let's see, we haven't really done a whole lot with tangent. We know that tangent in general is y over x. So what we're looking for is another point where it's the same x and y values, but the final fraction has to end up being exactly the same as what it was. And so what that means is that the, like in this case, what can we say about the x and the y right here at this point? Well, we can say that the x is a positive number because we went to the right, and the y is a negative number because we went down. So the other thing, so that means that down here is a positive and up here is a negative. So we need the same x and y values, so I'll just grab the 4 symmetric points to that one. It's got to be the same x and y, but needs to be negative when all is said and done, because that's a negative fraction. So if you're over here, those are both positive. If you're down here, they're both negative, and when you divide the two negatives by each other, it becomes positive. I need it to be negative. So it's actually this guy over here, because at this point, the x is now a negative number, and the y is now a positive number. And when I divide them, I'm still going to get something negative. Okay, so that means the other fundamental solution is up here. Negative 1.03 is that angle. I guess I'm interested in knowing this angle. Okay, so how do we find that angle? Well, if negative 1.03 is that green one, then it must be this green one as well. 1.03 is there. So that means that the black angle, which is the one that I actually want, must be pi subtract 1.03. Okay, so let's first make the negative of this answer, and then we can do pi minus that. Okay, so we get about 2.11. Okay, so that's our other fundamental answer. At this stage, and before we solve for x, we need to put in this plus 2 pi k. It's so easy to forget to do that. It's also easy to try to do it at the end. You cannot. So plus 2 pi k. And then we have to just do a little bit of algebra to solve for x. So let's first add 1. And I'll just go ahead and add 1 to this guy as well. And then divide everything by 2. Okay, and we've got our two answers, there and there. So I think that solving complicated trig equations is something that is challenging until you get the hang of it. It's a lot of steps, but I think it's a really important process. And so I'm hoping that you will practice a bunch in order to get better at this important process. The activity is down below. Give it a good shot before you take a look at the video.